Hello. So we continue our lessons in statistics, and now we move on to a new chapter, which is on bivariate analysis. And we will begin by introducing to you what is correlation and how it is done in social research. And we will show you how to conduct certain correlations using particular correlation coefficients, namely Pearson's correlation coefficient or R, and some other non-parametric measures of correlation. When we say non-parametric, that means that the assumptions that you need for Pearson's R, which is used for interval level data, are not met. So non-parametric measures are more applicable to certain types of data, no, that are not interval, that does not meet certain assumptions for Pearson's R. Okay, so this is the outline for this presentation. Now, some of this I have breezed through in a previous lecture, no, a previous meeting, but I will still go through them as a sort of a refresher. Okay. So first, what is correlation? No, correlation is a set of techniques, no, in statistics that you will need if you want to go beyond describing the data and actually make inferential analysis, no, as to the relationship between two variables. Now, remember, this is just a bivariate analysis, so we will keep it simple and more and easier. So we'll just, for now, look at the relationship between two variables. No, if you get to higher statistics when you pursue higher level education, then that's when you encounter um, measuring and describing relationships between not just two variables, but uh, a set, no, many predictors and criterions. So there. But in a simple correlation, such as we are about to learn, no, we are usually interested in two variables. And these two variables must be naturally existing. No? They are simply observed as they exist in naturally in the social world. No? So no amount or effort of control or manipulation will be done by you, by the researcher, by the experimenter. No, you are simply observing and recording, no, people's score, people's placement, people's classification on these variables. No, so I could give you an example. For instance, um, family income. No, you can't really subject family income to an experimental design because we just have families just have income, and the best method to get to know people's or families income is through a simple interview, no, a simple survey where you just record their response or record the value that they give you, and you just accept it as is. No, so that's an example of a naturally occurring variable. Another one is students' academic performance, no, or grades. So you simply need to get a hold of secondary data, no, perhaps the transcript of grades, no, a copy of students' grades from their university, and record whatever is written there. No, you can't manipulate the grades. No, you can assign people to an experimental condition for those types of variables. So there. So in correlation, you will require two scores for each individual. That's what you're trying to correlate. So you need two from the two variables that you are trying to measure. No? So one score will come from one variable, variable A or variable X, and another score will come from variable B or variable Y. So in correlation, we identify these scores as the individuals or the respondent score on X and Y. All right, and they are usually listed in a table, or you can also graphically represent them by plotting the scores on a scatter diagram or scatter plot. Okay, so in the scatter plot, the values for the X variable are listed on the horizontal line or the X-axis, if you still remember your high school algebra. And the Y values will be on the vertical axis. No? So that's your Y-axis. So let's look at an example here. Um, Here is correlational data showing the presumed association or relationship between family income and students' grades, as I've mentioned. Now, for a sample of N is equal to 14 high school students. Now, the points, the red dots on the graph are individual respondents or individuals. No? And yeah, by doing a scatter plot or scatter diagram, we can sort of eyeball and visually inspect to see if there are patterns or trends in the data for these two variables that are being correlated. Now, each individual, persons A to N, is represented by a single point, a single dot in the graph or the scatter plot. So that, as I've said, the horizontal position here corresponds to X, which is family income in this example, while the vertical position here is represented by Y, corresponds to their Y value, which is their students, which are the students' grade. So from this, you can visually inspect and see that there seems to be sort of a pattern or a trend, such that students who belong to families with higher income tend to, in general, have better grades than their counterparts who belong to families that have lower income. Okay, so that for you is a simplistic way of describing presumed relationships or correlations. No, notice how I'm still very tentative because I've not subjected the data to correlational analysis per se. I am simply eyeballing the data from the graph, no? But it is clear just by inspection that there seems to be a trend. No? Of course, not everyone in this sample will necessarily follow that trend. No? Some have very high income or very low income, but they still get good grades. No? Some have very high income, but they get low grades. So for instance, student M has a family income of $135,000. That's quite a lot. And their average grade is 89. Now compare that to student K and L, which have relatively lower family income than M. But their grades, especially student L, is higher compared to M. So yeah, there are some divergences in the data. But in general, if we look at this as a whole, the trend seems to be that the more your family income is higher, the more we can expect that the student's grade is high as well. Okay. So let's continue. Now, the correlation that we will be comprehending and will attempt to demonstrate is the most common use for correlation, which is describing and measuring straight line relationships. No? Um, and it's very straightforward. But in reality, no, when you examine data from different studies, you will find out that there are other forms of relationships. No, that hindi lang straight line or straight line relationships yung meron. It's just the simplest to understand, no, and it's the most basic one. But there are other relationships too, such as a curvilinear correlation, curvilinear relationship, wherein you know the data seems to suggest a straight line relationship in the beginning, but as uh, we look at the data more, we will find that the relationship begins to reverse itself, no? Such that from a straight line relationship, nag-iba bigla yung pattern, wherein one variable begins to increase while the other decreases. So in the beginning, perhaps both of them were decreasing. So pababa yung relationship. And then suddenly one variable picks up and uh, gets to increase while the other remains to decrease. So that's an example of a curvilinear relationship wherein it starts off, let's say, negative, but then one of the variable becomes positive. No? So the relationship will follow suit. No? It's a negative relationship in the beginning, but it becomes positive. Or starts out as positive, but it ends up being negative. All right. So what do we mean by negative relationship, positive relationship? So when we say that, we are describing the relationship in terms of certain characteristics, no? And we have three that are very important. The first one is existence, the second one is direction, and the third one is strength or consistency. So when we say existence, we are asking if does X and Y variables have an association or no association at all. No? And it's very simple to know if there's an existence of a relationship. You simply compute for a correlation coefficient, such as Pearson's R, and when you get a value that is lower than or greater than zero, no, any value that is not zero, you can say that a relationship exists. No? But if it is zero, there is no relationship there. All right. The second one is direction. Is the relationship of X and Y variable positive or negative? The third one is strength or consistency. So we ask here, is the correlation between X and Y variable weak or strong? Does the data fit perfectly on a straight line? Okay, so let's look at that one by one. So when we say existence, this is what we pertain to. A correlation is a numerical value that indicates a relationship between X and Y variable. No? So as I said, just simply look at if there's a numerical value that corresponds to the relationship by computing something, and the correlation coefficient that is, and you can already tell if a relationship exists. No? But as researchers, we are not just interested in finding out if relationships exist. No, to be honest, if you try to correlate certain variables, no, kahit the most unlikely relationships or pairs of variables, I would bet that you will find some relationship there. No, you will compute a numerical value for them. Let's say if you correlate height with I don't know, with political preference, mga ganyan, you will find some relationship there. But we are not interested in finding existence alone. We want to see the degree of association between variables. So we need to know the direction and the strength or consistency of the relationship. So for direction, and we look at the sign, no, of the numerical value of the relationship, because the sign of the correlation can either be positive or negative, and this will tell us a direction. If it is a positive relationship or correlation, the meaning of this is that the two variables tend to change in the same direction. No? So simply put, as x increases in value from one individual to another in the sample, your y will also tend to increase. When x decreases, y also decreases. Now, if we go back to a scatter plot depicting a positive relationship, you will see that the points, no, the individual points will travel upward. It seems that they're traveling upward from lower left, no, to your upper right. Now, for that one quadrant, it's traveling from lower left to upper right. That's when you can inspect and sort of assume that it's a positive relationship. Now, a negative relationship is the opposite. No, the two variables tend to go an in opposite directions, meaning there's an inverse relationship between the two. As x increases, y decreases, or as x decreases, y increases. And the pattern on the graph here is that the dots seem to be traveling downwards from upper left to the lower right. Okay. Now, strength. Strength of a relationship is also called consistency. No? And for a linear relationship, the data points fit perfectly on a straight line. Well, that is the assumption. No? Later on, you will find out that you, as the researcher, dictates or decides what type of trend, what type of relationship you're trying to fit the data in. No, as I've said, there are many forms of relationship. The most basic one is the linear trend or linear relationship. There are others. No, there's a logistic, there's a curvilinear, so on and so forth. So you get to decide that. But if you have a sense, no, based on the literature and based on your engagement with the data, no, as you study the data more and read through the data, you can decide if my data, your data, assumes a linear relationship. And you will be predicting there that the data points will perfectly fit on a straight line. That is, every time an x score increases by a point, the value of y also changes in a consistent and predictable manner. So pwedeng positive relationship wherein as x increases, the corresponding y scores also increase, or pwede rin namang negative relationship wherein x increases, no, for each and every individual, but y decreases for each and every one as well. No? And when we say strength, no, we are asking if the correlation is strong or weak. Because if it is strong, then a perfect or near perfect linear relationship between the variables exists. No, there's a super strong trend that you see in the data, like no contest, no debate. It's a perfect relationship. No, and your scattergram will suggest you that. No, kasi if you look at the data points, no, it's so easy to draw a perfectly straight line, and each of the data points will be hit by that line. No, the line will pass through the dots, and that's a perfect relationship. No, and that's a perfect correlation, which is always identified by a correlation value or correlation coefficient of 1, positive 1, or negative 1. No? If it's, as I've said, if it is a perfect and perfectly positive correlation, that's a positive 1.00. If it's a perfectly negative correlation, an inverse relationship, it's a negative 1.00. Now, that's a perfectly consistent relationship. Ibig sabihin, every score on X, kapag perfectly positive, every score on X as it increases, every score on Y also increases. Pag negative naman, let's say all X scores decreases while all Y scores increases for the sample. That's what we mean by a perfect correlation. No? Each change in X is accompanied by a perfectly predictable change in Y. No? And that's when you can say that the straight line that you have come up with perfectly explains the data. And it perfectly predicts in a straight line, which we will look at later in regression analysis, perfectly predicts and tells you what will happen to Y, given your knowledge of X. Yeah, but in reality, relationships are usually not perfect. No, both in social life and in correlational studies and analysis. No, sometimes, as I've also given us a side example earlier on, we are dealing with tendencies only, such that although there may be a tendency for Y to increase whenever X increases, sometimes the data does not fit that description perfectly. Sometimes the amount that Y changes is not always the same. No? Sa mga individuals na kasama sa sample natin, merong iba na hindi sumusunod dun sa trend na as X increases, Y increases in a very predictable and consistent amount. Others increases slightly, others increases a lot, while others remain as is, or others even decreases as X increases. So that's what I mean by not all relationships between variables are perfect. Occasionally, Y will diverge. It will decrease, slightly increase, and greatly increase. So, yeah. A correlation of 0, unlike the perfect correlation, indicates no consistency at all. When you eyeball the data in the scattergram, you can't seem to fit any straight line to the data points. There's little value in drawing a straight line or finding a straight line that will approximate all these data points, because the data points are very scattered, and are scattered randomly in the graph, and there's no clear trend. You could infer that the correlation is very low and it is very weak. And if it is near 0, then there's no clear trend there. Usually in correlational research, what we will find are intermediate values between 0 and positive or negative 1, which tells us the strength or consistency of the relationship. Now, speaking of the direction, your positive or negative sign, and your strength or consistency based on the value of your correlation. Always remember that those two things are independent. If you see a correlation that is -1 and a correlation between variables that is +1, both of those are perfectly consistent relationship. Those are very strong relationships kasi 1 yung numerical value nila, regardless of the sign. The -1 and +1 are perfectly consistent relationships. Okay, the same way with negative 0.90 and positive 0.90. Those are still strong relationships. No, there's a clear trend to them. Magkaiba lang sila ng direction, no? Because magkaiba sila ng sign. And also remember that correlations have a range, which is from -1 to 0 to 0 to +1. You can never be, you can never exceed +1, and you can never um, be smaller than -1. All right. Otherwise, there's a miscalculation there. So let's look at this. These are examples of different values for linear correlation. With A here, ito yung pinag-uusapan nating negative relationship earlier. And it's not just negative, it's a perfect negative correlation. An inverse relationship wherein as x increases, like this one, y is at its lowest. It decreases. For B, ito yung sinasabi nating there's no visible, no, or readily observable pattern or trend. The points are literally scattered all over the diagram. So this is either one, it does not assume a linear relationship or a linear trend. No, so there's no relationship at all. No, or perhaps it's not a linear trend, but another type of relation, another form of a relationship. For C, ito kanina inverse relationship. This one is a positive relationship because the points travel from the lower left to the upper right. Itong A, it travels from the upper left to the lower right, kaya inverse or negative relationship. Ito positive relationship, but it's not a perfect relationship, no? Because if I draw a straight line here, no? Not all, this is not a straight line, obviously, but I'm just sort of demonstrating to you. If I draw a straight line there, not all of the points will hit the straight line. So that's already that's a very crude, but an essential depiction of a perfectly linear relationship. This one is not. This is just a strong positive relationship because as you can see naman, when we have a straight line here, it seems that the points are clustered around it. No, it's very near the straight line. So a relationship definitely exists there. It's positive because of the pattern in the graph. And perhaps it's a strong relationship because it almost approximates a straight line. All right. Now, D, ito naman, once again, negative correlation. But it's a weak, relatively weak negative correlation because the points are very far apart from each other. No, it's almost B, but you can clearly see the direction here. No, so this is a weak negative correlation. Okay. So here, to help us, let's look at correlation coefficients and what they mean. No, we want a numerical expression of not just existence, but also direction and strength or consistency of the relationship. As I said, this ranges from -1 to +1. No, 0 is still a possibility if the variables you're trying to relate to one another don't really make sense or don't really have a tangible relationship to them. So a value of -1 and +1 denote a perfect correlation except that their direction differs. No? Ito ay perfectly negative correlation. This one is a perfect positive correlation, which when you inspect the graph, the pattern will be all the points fall on a straight line. No? When you draw a straight line, all the points will hit it. That's when you can say that a perfect correlation exists. Now, point 80 and positive point 80, most of the points fall along the straight line, no? Yeah, they're almost there, no? There's just a little distance from certain points, no? Certain individuals do not hit the straight line. And this is still a strong correlation, all right? Negative point 50 is moderately strong. We can still see a pattern, a trend in the data, but it gets a little more challenging to see the pattern. Point 30 more so, it's only a moderate correlation. As you come nearer to zero, the correlation becomes weaker. And when you inspect the graph couldn't tell you a trend. No, you couldn't really describe a trend just looking at the graph. So you might need to solve for correlation coefficients just so you can be sure. But yeah, near zero is a very fuzzy indication that there's a trend. When zero, as the previous illustration showed, the points are so scattered, you can't really see any direction that the points are sort of following. So yan, you will use this for Pearson's R and the rest of the non-parametric measures of correlation. No? So you will compute for a correlation coefficient and you will be asked to interpret the direction, the strength, and consistency of the relationship. So you can use this as a guide for that. Okay. So obviously, sometimes you will compute somewhere between 0.40, somewhere between 0.30 and 0.50, like 0.44, 0.49. So I will let you decide. No, but you need to justify it, of course, if that's a moderate or that's a moderately strong correlation. No, for me, my basis would be saan ba siya mas malapit? Is it near a moderately strong correlation such as 0.50 or is it near 0.30? So there. Now, interpreting correlations. I'll just go through this very quickly. First, no, let's not confuse correlation with causation. No, simply computing for the existence of a correlation will not tell you something about the cause and effect of these variables to one another. No, it will not imply or prove a causal relationship. No, but just because let's say you get a positive correlation between family income and student grades, it it does not suggest and it does not categorically tell you that family income causes students' grades. No, to be more exact, like a high family income will cause better grades. No? That's a causal statement. And we try to avoid that in correlation because that's not the purpose and that's not the scope of correlational analysis. That is, causation is very difficult to prove, no? Because of certain considerations, certain factors, no? So let's not use correlation as a proof of cause and effect between two variables. So for instance, the directionality problem. This is like the old age question of which came first, the chicken or the egg. The same goes for your variables. So which should I consider as the first variable? Because that's the cause, right? And which is the effect. So that's very difficult to prove in correlation. So let's not do that. Second is tertium quid, or as I've said, a third variable. No, as I've said, we naturally observe the variables in action in the social world and simply record it and analyze them using correlation. So we don't control or manipulate these variables, and therefore we can isolate them from their context, no? From their interaction with other invisible, extraneous variables that are in existence in that context. So it is possible that there's a third variable, a third, fourth, fifth, sixth. So a tertium quid that's at play that could be pulling the scores up on variable x and pulling the scores down in variable y. Also, there are certain mechanisms and mediators in the relationship between variables. So it's yun nga, kaya we go back to the point that causality is very difficult to assert and prove when you simply are correlating variables. And of course, as I've said, if you want to prove causality, no, or try to attempt to prove it, do a true experiment. No, by true experiment, what I mean is yung degree of control and manipulation mo is very strong, is very high, that you are really able to isolate variables. No, that if you state that you want to study variable x and variable y only, the true experiment will promise you that. No, but I'm telling you now, in human affairs, no, when you're dealing with human phenomenon or phenomena and you want to study them, it's very difficult to control and isolate variables, no, unless you do what some behaviorists in psychology did in the past, which I would say they sort of still not really failed, no, but it was an uphill battle or challenge to do exactly that. No? I think true experiments rarely work in the social sciences and in the humanities, no? Because that's the nature of being human for you. I think true experiments are easier said than done. And it's easier in the natural sciences, in the physical sciences. Now, when you're dealing with inanimate objects and materials and elements and compounds and whatnot. But for humans, no, and social reality, it's quite difficult. That's why in correlation we settle with naturalistic observation of variables. Not to say that we don't do experiments. No, in psychology we do that a lot, but we're very careful when analyzing and making conclusions about our findings from the experiment. You still have to consider tertium quid, directionality. I don't know if some of you have encountered this in your other classes, but ecological validity. So, yeah, construct validity, all those sorts of things. You need to sort of explain it. Now, even if you are proclaiming to conduct a true experiment where the degree of control is so high that you've managed to isolate the variables and just study them for their very nature. Yep. And in statistics, now we can compute for partial correlation. No, this measures the relationship between two variables while controlling the influence of a tertium quid by holding it constant. There. So some examples I have said is family income is related to students' grade does not mean that family income causes students' grade. No, we don't need to go purely and strictly quantitative to know this. No, from a qualitative, humanistic sense or perspective, we know that there are exceptions to this correlation, for instance, and therefore it's not really a very valuable causal statement. No, we know that some people who come from low income families do good in school. No, they obtain really high grades. No, they finish at the top of their class, mga ganyan, right? So that alone as an anecdotal example already debunks this. No, so that it's therefore more problematic when you um, imply causation in a correlation finding. All right. The same way with growth in churches is related to higher crime rates. Crime rates. It does not mean that uh, as churches are erected in a place, more churches are erected in a place that the the crimes that are committed in such place increase, causes the increase. No? I think I gave the reason why that it turns out a tertium quid, a third variable explaining the relationship, no, or shedding light to the relationship is the increase in the population. Now, as more people populate a place, you will observe a plethora of basically a melting pot, a plethora of people from different backgrounds and therefore different religious beliefs and practices, and therefore kakailanganin ng mas maraming churches, right? That explains why there's a growth in churches, and at the same time, bakit mas maraming crime? Well, you could say that, just like in the case of a city, the more people populate the city, there will be more variation in the population, no? You will find more individuals that are inclined to commit crimes, no? So yeah, that's what we mean when we say don't confuse correlation with causation. Second, no, in interpreting correlations, let's be cautious because correlations are greatly affected by range restrictions. No, the range of scores represented in the data. No, as much as possible, when you're attempting to do correlational analysis, try to have the full range of possible values. So when you study a sample, make sure that the sample within the group varies. So for instance, in this graph, I think this is about the correlation between creativity and intelligence. So our student, no, this is his sample. No? At the end of his study, he did not find any significant correlation between creativity and intelligence. So it seems that there's no pattern there that we couldn't really describe if intelligent people are more creative or creative people are more intelligent. So the reason for the results is the example here only included respondents that belong to a very restricted range of intelligence level. I think the example that was given was, this is the scatter plot for creativity and intelligence for college students. And you already know that, people who go to college more or less have the same IQ, no, or belong to a very limited range of IQ. But when you open your study to more people beyond the college population, you will find that there is actually a relationship there. And there's a positive relationship, moderately strong positive relationship or strong positive relationship there. Because as intelligence increases, creativity also increases. And that's what we mean. Let's not overgeneralize the results of correlation beyond the range of data represented in the sample. So for example, it's really important to be context specific. So if the student declared that this is for college students, then yeah, this will pass. There seems to be no correlation. No, but already we know that it is flawed because the intelligence levels of those who were randomly selected in the sample were more or less the same. So yeah. Okay, and last, outliers have a very huge effect, a dramatic effect on the value of a correlation. No, if you remove the outliers, it can alter your results significantly because outliers are individuals whose scores on either X or Y are substantially different. No, so I'm not saying outliers are always high on X or high on Y. They can be very low on X or very low on Y. And therefore, hinihila nila yung statistic, no? If you still remember descriptive statistic, they pull the scores such that they influence the pattern that you will see in the data. That's why some researchers employ data cleaning, no, or others perform data transformation. So yung una, data cleaning, others will remove the outlier and justify their removal from the data. No, usually the reason is because outliers conflate the results, no, misrepresent the general trend, and therefore researchers justify that they need to remove the outliers so that we can see a clearer picture of the aggregate. No, and that's perfectly acceptable as long as you state and justify your reasons concisely. No, in your findings, in your report, you need to say and explain why bakit tayo nag-data cleaning, bakit may mga tinanggal tayo. So that's one. Others perform data transformation. Data transformation happens when, well, it's from the name itself. When you feel like, let's say, for instance, the linear trend, no, or the linear relationship does not seem to fit your data, no, because of, let's say, outliers. So you do data transformation and turn it into a curvilinear trend or a log logistic trend. So that's how, in a nutshell, data transformation works. And it's completely acceptable in statistical research, as long as, once again, you state your reasons why and justify why you need to do that. No, so you're not essentially manipulating the data or manufacturing the data. You're simply converting the scores into another form, no, that will make sense more given the existence of your raw scores now with your outliers and whatnot. Okay, next. Now let's go to Pearson's R. So what is Pearson's R? So this is the first correlation coefficient that you will encounter. Its complete name is the Pearson's product moment correlation coefficient, and it's a large number of coefficients. Now, you will see that later in the Pearson's R table, which measures linear relationship between two variables. No, this will go back to your lesson on z-scores because it is a mean z-score product of the two variables and measures the amount of variance that can be accounted for by a straight line. No, so don't be confused by this jargon with this terminology, the amount of variance that can be accounted for by a straight line. It's simply telling us that yung straight line ba na mapoproduce and makocompute natin, can it explain the entirety of your data? No? Can it provide a very succinct, a very good description and measure of the data? That's all there is to it. No? Na, our scores are different, right? The sample contains varying scores. There is variance in the sample. Now, will a straight line, no, a straight line equation be able to successfully, succinctly, and accurately explain the variance. So that's all there is to it. So the Pearson's R provides knowledge of how two variables relate to one another, which can help in predicting what will happen to the other variable when one variable increases or decreases. All right, so here are certain assumptions that we need to meet first before using Pearson's R. First is that the variables that you want to measure must be normally distributed. That way we can use that we can use the critical values that the Pearson's R has provided us. Second, linearity. As I said, there are other forms of relationship. Make sure first that the data is linear, because if it is not, then whatever you compute with the Pearson's R becomes questionable. It diminishes. Like for instance, you have two variables and apparently they really have a curvilinear relationship in existence, but you still insisted on using Pearson's R. Now you'll be surprised because you will find that R will be 0 or very low. And the reason for that is not because you miscalculated, but because to begin with, you were dealing with curvilinear data, curvilinear trend. And therefore, mababa talaga yung linear trend, yung linear coefficient. Next, data must be independent, and to ensure that we simply do random sampling. Next, interval or ratio level data dapat. Otherwise, you use the non-parametric measures of correlation. And fifth, as I've just discussed, it is better if the data comes from a not so restricted range, when it is unbounded. So this is the simple step-by-step for computing Pearson's R. This is the formula. As you see, it's once again a ratio. It's like an expanded z-score formula, and each of these components, summation of xy, sum of x, sum of y, sum of x squared, and sum of y squared, you will be able to arrive at by making an expanded data table for Pearson's R, which I will show you later. And of course, degrees of freedom, it's n-2 because we are dealing with two sets of scores. If you remember the paired samples and the independent samples t-test, they have a very similar degrees of freedom formula because two sets of scores ulit yung kino-compare natin. Well, this time we are correlating. Then let's do a simple decision rule that whatever you compute for R, if it is higher compared to the R critical that you will find using the DF in the critical values table of Pearson's R, then you retain or reject HO. So kapag mas mataas si R here compared to R critical, you reject. If it is not, you retain. And then it's very important to interpret the direction and magnitude of the R computed if HO is rejected. Kasi nga, we want it to make sense to whoever will be reading or using our findings. And later on, I will show you that we also need to compute for a certain R squared. So it's simply R, but you square it. That's what you call the coefficient of determination, which will go back to the idea of this. How much does X explain the variance in the data? Okay, so yeah. Before we move to the sample problem on Pearson's R, I'd like to introduce to you already the non-parametric measures of correlation. Once again, you use this for if your data is not interval and ratio data, and if you're not sure if the variables are normally distributed, if it is not interval or ratio data. You use non-parametric measures. No? This is similar to chi, if you remember chi. No? So the first one is Spearman's rho, no? And which you use for ordinal data. When you're dealing with ranked data, no, not actual values, numerical values, or if you prefer transforming interval data into something categorized and ordered, you use ordinal data, no? And this is its formula, and to get the elements of the formula, you need to do an expanded data table for Spearman's rho, wherein you basically how do you call this? Rank the scores. Rank the individuals in your sample base, rank them on X and rank them on Y, and get the difference in the rank between X and Y variables. The next one is Goodman's and Kruskal's gamma. Once again, this is for ordinal variables that are cross-tabulated. No? And you will be dealing here with number of agreements and number of inversions, which I will try to explain later when we encounter the sample problem for gamma. And then just like Pearson's R and Spearman's rho, you can test the significance of the gamma coefficient using this. All right. And lastly is the phi coefficient. This one is for nominal data that is once again cross-tabulated, and it's on a 2x2 table. Now, if you remember chi-square. So this is an extension of a chi-square test, and that's why it has the same degrees of freedom. So I will show you how we will go through the formula and its elements when we encounter the sample problem for phi coefficient. So, yeah. Are there other non-parametric measures of correlation? Yes, but I've chosen to limit it to 3, because the other examples or other types of non-parametric measures of correlation are an extension, an alternative version of what I just gave you, the Spearman's rho, the phi coefficient, and what was that? The gamma, the Goodman and Kruskal's gamma. So there are other measures like the Kramer's V, the point by serial, the Kendall B, the Tau B, the Tau C. So there are a lot more, and I'll trust you to look that up, and more or less you will follow the same logic as these 3. But for our class, let's settle with these 3. So now we will be solving problems for the next video. I will be ending the video right here. We will be solving these 4 problems. All right. Yeah. So for now, I'll be ending the presentation here, and please go watch the next video, which is the demo video for solving correlational problems. All right. So, yeah, thank you so much for listening or watching.